We're going to take a look at one thing that is partially explained by the Bernoulli effect. It's a powerful engineering concept, which is why airplanes fly. And lift on a wing is actually a result of of four different factors. It's quite complex, but there are two factors that you're prepared to understand right now, and they are really significant factors in lift. The first factor is momentum change. So the wing, maybe imagine this is a wing at a slight upward angle relative to the flow. The plane is taking off; it might be tilting, slightly up. So the flow, if you imagine the flow coming in kind of straight as the plane is moving, from this case from right to left, that wing is going to divert the air momentum downward as it just simply deflects that air. And as that happens, that's going to cause a momentum change downward in the air, which is going to cause an upward force on the wing. So that's pretty obvious, and you know that from playing around with all kinds of things that, air resistance pushes things up if you tilt them upward as you move them through air. But the other effect, which is really a result of the Bernoulli effect that is also real, is that the curved upper surface of the airfoil, and if you notice wings have this shape, they tend to be flat on the bottom or close to flat on the bottom, and on the top they're curved. And the reason for that is basically to capture this Bernoulli effect. The flow, if you imagine that the airflow is coming straight in here. Now imagine the plane is traveling at some constant altitude just straight through the air. The air is, approaching the plane at some velocity v0 or whatever speed the plane is traveling at. The air traveling under the wing is just going to go straight through and go right by the wing at speed v0 because the bottom of the wing is flat. But the air that's going to pass over the top of the wing has to travel a longer distance. And yet mass flow says the same amount of air has to enter as leave the system. So all the air that enters has to all get past this wing and get out at essentially the same time, which means that the air above the wing is going to have to be traveling faster on average than the air below the wing. Another way to see that is that the amount of air that travels through that control surface has to be the same as the amount of air traveling through this control surface if you imagine that the air has split right in the middle at this wing front, and that obviously this distance here is slightly less than this distance here because this wing curves up, which means that this air, in order to have equal mass transfer through both, this velocity up here is going to have to be greater. If the velocity is greater, the Bernoulli equation says, and you know this now, in this case, if you're looking at the top and the bottom of the wing, that the top and the bottom have to have the same Bernoulli constant because they're part of the same flow field, and there's no heat generation in between. Of course, there actually is. There's friction on the wing, but we're neglecting that. So we say not top and bottom. So the GZs are negligible. This is air. We're talking about very small differences in height. So we're not going to worry about that difference. But that tells you that the pressure at the top of on the top of the wing is going to be equal to the pressure on the bottom of the wing plus rho times the V at the bottom squared over 2 minus V at the top squared over 2. So I've just solved this equation for P at the top. And that clearly means that V at the top is faster than V at the bottom. That means the pressure at the top is going to be less than the pressure at the bottom because V top is negative, V bottom is positive. So if V top is larger, that's going to cause a subtraction term here. So P top is going to be slightly less than P bottom. It's going to be less by that rho times the difference in velocity squared over 2. And if the pressure at the top is less than the pressure at the bottom, that means there's going to be a pressure force pushing the wing upward. And that is the Bernoulli effect that helps explain lift. But it should be said that the momentum explanation and this Bernoulli effect do not fully explain lift on a wing. In fact, to solve real airplane design problems, and modern aircraft designers rely almost entirely on computational fluid dynamics, solving the real equations of fluid flow. As you can see, obviously, The Bernoulli effect, as we said, is really only good when there's no friction. Well, there's definitely going to be friction on the wing. It's just confined to a small area near the wing. So the Bernoulli effect does give us insight as to what's going on. You do see a pressure difference between the top and the bottom of a well-designed airfoil, and it does provide upward lift. The main takeaway in terms of all use of Bernoulli is that whenever you have a faster velocity, you have a lower pressure. And we're going to see that in other examples, I think, including in an experimental system that you're going to see.